How you doing? I'm Mr. Rose, and today we're going to continue our discussion about electric potential, specifically equipotential surfaces. I have an example all written out to start, which is a little bit of review of last time, a quick overview of what's going on here. We know there exists an electric field on Earth, and that electric field is approximately 150 newtons per coulomb in the down direction. Notice I forgot my word down. I just threw a little arrow over there. And that electric field is existent really near the surface of the Earth. Now, the Earth is also being bombarded by rays, cosmic rays all the time, from like the sun. And because of that, we can knock loose electrons out of the atmosphere. So the question that I have written up is, if all of this is taking place and an electron is released, just knocked out due to one of those cosmic rays, and moves vertically, the things that I want to know is, what is the change in electric potential energy when one of those now free electrons is released and moved vertically upwards, 520 meters. The second thing I'm looking for, what is the difference in the electric potential when the electron moves? The key to this, both questions again sound the same, but remember, electric potential energy and electric potential are two different things, so I'm looking for both of those things. How do I go about doing that? Well, start with all the things that I know. I know that by definition, work is my change in potential energy. I misspoke in our last lecture, and I called that conservation of energy. We know this is actually the work energy theorem. I also know that work is F dot D, a force times the distance, or force times distance times cosine theta. And I know that the electric force is just charge times an electric field. I put all that together. I know work is F dot D, which is QE times D. And now it's simple, just substitution. This is a lower level question. I know the work is my electron times my electric field times the distance I'm moving and times the cosine of 180 degrees. And that's because I defined my electric field going down towards the center of the Earth, and I'm moving my electron up, so they are 180 degrees out of phase. Throw all that together and I get a work of negative 1.2 times 10 to the negative 14th joules. Means I need to do work up against the field in order for that to happen. Next, I want to find out what my change in electric potential is. Well, just by definition, my change in electric potential energy is equal to negative Q times my change in electric potential. That is my definition of electric potential, which is what we were talking about last time. And now I have a change in electric potential of 4.5 times 10 to the 4th volts. So that's a nice, easy way to see how all of this relates. Today, we're going to continue our discussion about electric potential, specifically with these equipotential surfaces. So by definition, adjacent points that have the same electric potential within an electric field are equipotential surfaces. Those surfaces can be real, or they can be imaginary. For example, we've had a concept like this before. Let's say I have a ball at spot A on a table. Let's assume there's no friction. Well, I take this ball and I move it from A to B. That doesn't take any work. Net work equals zero, again, because I said it was frictionless. This is the same concept with electric potential. If I can move a charged object from point A to point B and my delta V, electric potential, never changes, then by definition my electric potential energy would never change, and I can move for free. In other words, my work would be zero. Here I have a quick little example of what an equipotential line would look like. Equipotential lines, here I have a charge, and we could know that that charge is positive because my electric field lines are coming out from it. Remember, electric field is the way a positive test charge would move. And those are about the same distance away, and more importantly, they're perpendicular to those lines. Anywhere where I drew an electric field line, this equipotential line would be perpendicular to my electric field line, which means if I move from there to there, my delta V would be zero. If delta V is zero, or if V naught is equal to V, obviously, the work done is equal to 0 joules. I get to move around for free. Very similar to when we talked about gravitational potential energy. So if there's no delta V between if there is a delta V between 2 points, and they happen to be in a field, then you can find an electric force vector. How are we going to do that? Well, the same way I found that my work was 0, I can find that my work is Q times delta V. This time delta V is not 0. I can start to do this. how does that relate to my field? I've got a whole bunch of things written up here with no electric field. So how do I figure out what my relationship to my electric field is? How am I solving for that? Well, it's easy. At any point in an electric field, there has to be a force. If there's an electric field and a charged object in that, there has to be some kind of an electric force. We know that's going to exist. Well, if I move that just some small amount, then I'm going to have very, very small electric potential, delta V. If I have a small delta V, that means I have a small amount of work, a differential amount, so to speak. So based on what we know work by definition is F dot D. Well, I know my very small dW is equal to negative F dot ds. I know F is equal to negative Q times Z. So now I have my differential work is negative QE dot ds. I can pull out my constant, and now I have a nice simple example, or a nice simple form rather, of work is equal to negative Q times the antiderivative, summing up all of those small little ds's of E dot ds along my path. I might be able to see here now, if I simplify this a little bit, work divided by charge, just bring that over, is equal to the antiderivative of E dot ds. This will hold true whether my field is a constant field or a non-constant field. Now, here I have work divided by charge, again by definition, is an electric potential. So, if I know work divided by charge is an electric potential, I can then say that my change in electric potential is adding up all my little pieces from the initial to my final through my electric field along some path. If I start at some initial position, 0, and by that I mean infinitely far away, where if I say I is equal to infinity, then my initial electric potential is 0. A very simple equation, V is equal to negative antiderivative of E dot ds. This will give me the potential at any single point. I can, if I have a change or 2 points, I can do the same thing and have a delta V here. Obviously, these two things say very similar things. Well, to show that this is path independent, at least to start off, it's easiest to start off in a uniform field. Let me get on screen here, in a uniform field. In this uniform field here, I have electric field lines going from the top to the bottom. I know my formula, delta V is equal to negative E dot ds from my initial to my final position. And if E is constant, I can pull that out of my antiderivative sign, right? Because it's never going to change. So I can pull that right out. Now I just have my initial final position of E dot ds. Now again, just like energy, it should be path independent. We've done it a lot of times for mechanics. This should be no different. So to start, I have an I, an F, and then I have this intermediate spot A. Look at the left side. The left side is really easy, just going from I to F. Well, my change in electric potential is negative E dot ds. I can pull my E out, E cosine 0, because it's moving in the same direction as my electric field. The cosine of 0 is 1. I get my change in electric potential to be negative E dot d. Well, what if I go from I to A and then from A to F? That's what I have over on the right side that follows down here. Going from I to A, I'm moving perpendicular to my electric field. That, by definition, was my equipotential surface. Maybe I don't remember that. So I know that delta V is E cosine 90, right? Same exact thing I did here. Cosine 90 because I'm moving perpendicular to my field. E cosine 90 times the integral of ds. Cosine of 90 is 0. So I know my potential from there to there is 0. Well, now what if when I'm going from A to F? Well, from A to F, I have a little picture here where I'm moving that distance S. I know from my picture that angle is 45 degrees. That's going to come back to help us later. My change in electric potential, initial to final, negative E dot ds. I pull out what I'm allowed to out of my antiderivative or integral sign. My change in electric potential here, delta V, negative E cosine 45 times the antiderivative of ds. The antiderivative of ds is just S, and from my picture I can see that S is actually equal to d over cosine of 45. Simple substitution, delta V equals negative E cosine 45 times d over cosine 45. Those guys cancel, and then when I have squeezed right on the bottom here, delta V equals negative E dot d. So I can see that this is the same as if I went from A to B. In that uniform field, my electric potential is constant. And, I'm sorry, not constant. In my uniform field, my electric potential, delta V, is not constant, but it is path independent. That's all I have for you today. Please like, subscribe, comment, anything you would like. No electric potential puns I got going on today, so I will just see you next time. Thanks for watching.